In the next 5 minutes, I'm starting the class at 11:35 am. Inform your friends to join as early as possible. Okay. So in the previous class, we just saw the behavioral statements or the statements which would be helpful for writing the behavioral code. So like, we have discussed the two programs. One is the T flip-flop and the D flip-flop. So in today's class, we'll be dealing in general with the writing of the other two flip-flops like JK and the SR flip-flop. So before that, as I suggested you to verify a site. So this is a site called as chipverify.com. So chipverify.com is the one site which will provide you one-stop solution for all your doubts. Okay. So the flow is also like a syllabus only. Go through this website. Okay. So one simulation example will be shown here. Okay, there are two kinds of procedural blocks: initial block and always block. This is an initial block which starts at time 0 nanoseconds. So you can see here multiple statements you can include by using begin and. The simulation time also you can see here A will proceed at 0 with delay 10 is assigned here. AB your type is register with the 20 millisecond delay. B will be having the value. You can see here initial A is equal to 2 tick 1 0. First it will have this delay 2 tick 1 0 after initially. So then now we can see B here. B at 20 it will remain silent. After 20 it will be having 1 1. Okay, this is how the things will execute in Verilog also. Then coming to the next point, then after 10 A will be appeared with 1 1, B will be appeared 40, B is 1 0. At 40 means you have at 60 it will appear. Okay, at 60 you can see that it is changed to 1 0. Then $60 it will finish. Simulation is over at 60 nanoseconds. So this is how the program will evaluate. So this is how the program will evaluate. Okay. So I'll go to the next topic. Verilog in a nutshell, if I put what happens here, all behavioral code is written inside module and end module. So in a nutshell, if I want to define this behavioral modeling, all behavioral code is written inside inside the keyword module and end module. So whatever digital design that you intend to create, it will go inside a module block, and it may or may not have ports defined. Allow signals to enter the block as input and escape the block as output. So we can, in a nutshell, if I put it, a behavioral code is written inside module and end module. So whatever digital design that you need to intend to create, it will go inside a module block. It may or may not have the ports defined. Allow signals to enter the blocks as input and or escape the blocks as output. Module, the empty module in the example below is test bench. So this is a test bench. You can name it whatever you like, except that it should be an alphanumeric and can contain underscore also. Module test bench. So now module inputs outputs irrelevant kontella. We can define a simple module like this as stated in the diagram here, as shown in the diagram here. Module test bench, end module. Let's look at another module. It has few signals like D, clock, and reset declared as inputs and Q as output. So you can see here I'm trying to define a D flip flop, D reset clock Q, or in the same way you can write it in this fashion also, D reset B clock and output is Q. So this is how we have to define the module inputs and outputs. So data types I can use either register or wire. Register or wire. A register data type is used to hold values, output values like a variable, while a wire is just an analogous to an electrical wire that it has to be driven continuously. So now I'm trying to summarize the things. So typically wire is used to connect between multiple modules and other signals. So here you can see here module test bench, register D, register reset underscore B, register clock, wire, Q, end module. Verilog has three basic blocks: always, at condition, initial, then always will be executed when the condition is satisfied. Initial is executed only once when the stimulus begins. Assign, left hand side equation is equal to right hand side equation. The value of LHS will be updated whenever RHS is changed. There are few rules to keep in mind when writing Verilog. Register can be assigned to only in initial and always blocks. Initial ಮತ್ತೆ always work register na assign ಮಾಡಬಹುದು. Wire can be assigned with a value only via assign statement. If there are multiple statements in initial or always block, they should be wrapped up in begin and end. So if I want to write the test bench here, module test bench, register D, register reset underscore B, register clock, wire Q, initial begin D is equal to 0, reset is equal to 0, clock is equal to 0, 100 finish. The finish at 100 nanoseconds finished. Begin ಇದೆ end ಮಾಡಬೇಕು. Always begin clock is equal to not clock end module. End module. Note the following from the example shown above. Since there are multiple lines for initial block, you have to use begin and end. Begin ಮತ್ತೆ end use ಮಾಡಿದ್ದೀನಿ ನಾನಿಲ್ಲಿ. Signal D, RSTB and clock are assigned with initial block because they are of type register. They are of type register. Code inside the initial block will be executed 0 nanoseconds. It is start of simulation. So initial ಅಂತಂದ್ರೆ it will start simulation at 0 nanoseconds. You have to keep that in mind always. If I say it is initial, it will start the execution at exactly 0 nanoseconds. Okay. Clock is equal to not clock. Yeah. Since there is no condition for always block, it will run like an infinite loop in C. Always ಅಂದ್ರೆ ಯಾವಾಗಲೂ means it will be in a infinite loop. Always you are late by 10 minutes likewise. Hash is used to represent time delay. 10 tells the simulator to advance simulation time by 10 units. Clock is equal to not clock will toggle the value of clock from 0 to 1, 1 to 0 respectively for every 10 time units. Dollar finish will stop your simulation. Dollar finish will stop your simulation. So this is the Verilog in a nutshell. ಒಂದೇ ಇದರಲ್ಲಿ ಹೇಳಬೇಕು ಅಂದ್ರೆ ಈ ತರ ಆಗುತ್ತೆ. So then we'll go with the Verilog blocking statements. There are ways to group and set statements together that are syntactically equivalent to a single statement and are known as block statements. They are called as block statements. Why? Because there are two kinds of block statements, sequential and parallel. Sequential statements are wrapped using begin and end keywords and will be executed sequentially in given order, one after the other. Delay values are treated relative to the time of execution of the previous statement. After all statements within the block are executed, control may be passed elsewhere. Initial begin hash data 10 8 tick HFE means I am trying to write a hexadecimal data here at this point of time. Hash 20 data is equal to 8 tick H11 end. Module design 0 bit 32-bit data. Initial block starts at time is equal to 0. Initial begin. So there are multiple statements that I have to use begin. Hash 10 data is equal to 8 tick HFE. Display time is equal to %0t. Data is equal to %0x %0h time comma data. So I am to display my time and data. That's why I am trying to write this statement. After 20 time minutes, data becomes 0x11. Hash 20 data is equal to 8 tick H11. Display time is equal to %0t. Data is equal to 0x %0h. Dollar time dollar data and end module. So simulation log. So log will be like this. So a parallel block. So you can use this parallel block also. So I'll show it in a conceptual way. Just wait. A parallel block can execute statements concurrently, and delay control can be used to provide time ordering of assignments. Statements are launched in parallel by wrapping them within the fork and join keywords. One second, I'll show you a video. Yeah, just
EDA Playground. Today we're going to be covering blocking and non-blocking assignments. Both of these assignments get executed inside sequential blocks. So sequential blocks are the ones that are surrounded by begin and end statements. And blocking assignments, just like their name, block the execution. So they cannot allow the next line to execute until the current line finishes. Non-blocking assignments, on the other hand, do not block the execution. So if you have a bunch of non-blocking assignments, they're all gonna execute at the same time. So let's move on to an example. We have a test module here. We're gonna define some variables, some fields, A, B, C, D, E, and then we're gonna create our sequential block here, surrounded by begin and end. So let's assign A to 0. Let's assign B to 1. Let's assign C to be B. Let's delay D by 15 time ticks and then change it to 1. And then let's delay E by 15 and then change it to 1 as well. And at the end, we're going to increment A. And then we're going to wait a little bit longer, 5 time ticks, and then call our finish statement. So let's see what happens. We're gonna look at some waves. So let's create a dump bars here and click open EP wave. Let's run it, and our EP wave has been opened. So A is 0 as expected at the beginning, B is 1, C gets assigned to B, which is also 1, D becomes 1 after 15 time ticks as expected, and then after 5 more, E becomes 1, and at the same time we increment A, which goes from 0 to 1. So this is an example of the blocking statement. So they all execute in order, and according to the waves, everything's happening as expected. So let's change it up and let's do non-blocking. So we're gonna try to keep the same code, blocking and non-blocking code in the same code base, and I'm just gonna use if-defs to differentiate between which one's running. Okay, so we did blocking first, which is a simple equal sign. So now we're gonna do non-blocking. Non-blocking. This is else, and then we're gonna end it here. So once we set this define, the code inside here is gonna execute. Of course, we now need to change it. So I'm gonna try to change all of these now to non-blocking statements. So they're gonna execute all at the same time in parallel. One thing to note here is that this delay, which by the way, delay is non-synthesizable, so it can only be used in a test bench or for modeling. So in order to make this statement non-blocking, this delay should be moved to the right-hand side here. So basically, this will have the effect that D will become 1 after 15 time ticks. Let's do the same for E, but now instead of 5, it really should be 20 because this is going to execute all at the same time. So let's change this to 20 just so we can make it look similar to the previous code. And we'll leave this alone for now. Now, since these all execute in parallel at the same time, we need to increase our delay here because the simulation is just going to stop after 5 time ticks, but we wanted to keep going. Last time it went on for 25, so let's change this to 25. All right, we have our code here, so let's set a define on the command line. Define non-blocking. Okay, and this is non-blocking. Let's run it. And right away you see some interesting things here. First of all, A is always X. Well, the reason it's always X is because we drive it to 0, and at the same time we try to increment it, which is a conflict, and this creates an X. B is 1 as expected. C is also X. Now why C X? Well, because when this statement executes, B is not 1 yet, because these two statements execute in parallel. So B is initially X, and then when C gets assignment from B, C becomes X as well. So it never changes from X. And then D changes to 1 after 15 time ticks, and E changes to 1 after 20 time ticks. So let's try to fix this a little bit. So we have this issue with A. So I'm not gonna do a complete fix here. I'm just gonna clean up a little bit. Obviously, this is an issue here, and then this is also an issue. So we're just gonna do a quick cleanup here. Okay, now we have something close to the previous simulation. The only thing is that A doesn't get incremented at time 20. So this is the basic idea of blocking and non-blocking statements. Now I'm gonna demonstrate their use in a simple always block. So I'm gonna do a simple dot designer to test. It's gonna have a couple inputs: clock, reset, and it's gonna output some values. So it's gonna output FGH. So I'm gonna have an always block, always at posage clock or posage reset, because we're gonna need to reset this this module, begin and end. So if reset, we're gonna set some defaults here. So we're gonna set F to 5, G to 8, and H to C. And then when the clock actually fires, we're gonna swap all of these around. So we're gonna do G becomes F, H becomes G, and then F becomes H. G of H. Now, as you can see, there's obviously a problem here because we're using blocking statements. So they execute in order. So by the time we get to here, H has now become the value of G. So I'm going to run a sim to demonstrate this. First, I'll hook it up over here to the test bench. Wire FGH. And then I'm going to use the proper connection by name here. Reset. And F G H. So that's going to hook it up. Now we need some stimulus. We're going to put the stimulus up here.
Clock is equal to not clock.
Clock to 0. And now for reset, we're actually going to use a non-blocking assignment. We're going to initialize it to 1, but then we're going to change it to 0 after, let's say, 5 time ticks. And then we also need a free running clock. So we're going to have an always, I'm going to give it a period of 4. Always clock. Toggles. All right, let's run this and see what happens. Okay, we have some issues here. Okay, we forgot the end module back here. All right, let's try it now. All right, we have our clock, and then we have FGH. Reset. When reset's high, they all get set. But then something's weird's happening. Let me double check to make sure it looks fine. So in our attempt to swap all of these, obviously G got assigned to F, which is 5, and then H got assigned to G, which is also 5. So they all got changed to 5. So before trying to figure out how to fix this, let me show you how to do this with a non-blocking assignment. So I'm gonna do the if def here, if def non-blocking, which we already have set, so this code is going to execute. Make a copy of this, and if should be else. Let me change this all to non-blocking here. Now we're going to see what we expected, all of these to be swapping every clock cycle. We have non-blocking already set back here, so let's run it. Okay, 5-8C, C5-8, 8C5, so they're swapping each other's values, once again because non-blocking execute at the same time. Okay, so let's see how we can fix the issue we had with the blocking assignments. Well, in order to do the swapping with the blocking assignments, we're going to need a temporary variable. So we're going to create a temporary variable 3 to 0, call it temp, and then let's try to fix this here. So we're going to assign temp to we have FGH here, so let's assign temp to H, and then G, and then let's reorder this a little bit.
Good morning.
F becomes H, H becomes temp, um, F becomes temp because it's the same as H, H becomes F, let's reorder this, and then G becomes F, G becomes F, H becomes G, so at this point I think this looks correct, so let's try it out and test it. So let's run it. We're running non-blocking down here. Okay, so this looks like it's behaving as expected. So that was the fix using the blocking. That's what we're using, the blocking. Just to verify we're using the blocking, we can expand our scope here, run it, and then we should be able to see the temp variable here. As you can see, the temp variable is changing down here. Okay, this concludes this tutorial on blocking and non-blocking statements. Thank you for watching.
Okay. So I guess you got a glimpse of what is non-blocking and blocking statement. There is one more video. So you can see here, I'll just share it.
So we have been
Hello?
talking about various kinds of assignment
Hello?
statements in Verilog. So recall we talked about the continuous assignment statement using assign. Then we talked about the procedural assignment statement. So looked at several examples where inside an always block or inside an initial block we can use various kinds of assignments to variables. These are called procedural kind of assignments. Now, broadly speaking, these procedural kind of assignments come in two different flavors. So, in this lecture, we shall be starting our discussion to clearly distinguish and try to find out when and under what conditions should we use which of these two options or alternatives. So, the topic of our lecture today is blocking and non-blocking assignments. These are the two types that I was talking about. Fine. So, These assignment statements fall under the broad category of procedural assignments. So, what do you mean by procedural assignment? Procedural assignment is an assignment, an expression which assigns some value to a variable, which lies or figures inside a procedural block. In Verilog, a procedural block can be either initial or always. Okay. So, these kind of procedural assignment statements can be used to update variables only of these types: reg, integer, real, or if you have a time variable which keeps track of time. You see, you cannot have a net type variable on the left hand side of a procedural assignment. This is the restriction. So, if you are using some variable to assign a value inside a procedural block, they have to be one of these data types. Now, you see, there is also a very clear difference from the continuous assignment type. See, in continuous assignment which we had seen earlier using assign, let us say we write assign a equal to b plus c. Here, whenever the value of b plus c changes, the value of a will be immediately changing. It will be directly driving this net type variable on the left, and this net type variable on the left of this assign statement do not have any facility or capability of storing this value. That is why we call this as continuously driven. As b and c changes, a will be continuously changing, right. But in contrast, for a procedural assignment, there is an important difference to be remembered. The value that we assign to a variable, this remains unchanged until you assign some other value to that same variable again. Okay. So, there is some notion of storage or memory associated with the variables that you use here. So, once you assign some value to a variable, the value will remain unchanged until you again assign it to some other value. So, this is the difference from assign which I just now talked about. So, broadly speaking, this assignment statements inside procedural blocks can be blocking or non-blocking, and they are denoted by the assignment operator. Blocking is denoted by equal to, non-blocking is denoted by the arrow symbol less than equal to, this symbol. This means arrow. Okay. Fine. So, the rules for a procedural assignment statements are as follows. So, I already talked about that the variable on the left hand side should be one of reg, integer, real or time. This is of course a constraint. Not only this, on the left hand side we can also have a bit select of one of the variables of this type, like we can write sum 15 equal to something, right. This is one particular bit of a data of this type, or you can also select a part by specifying the index values like IR bit numbers 26 to 31 equal to something. This also you can mention, or you can concatenate one or more of this by enclosing them with the within the curly braces as I mentioned earlier. So, you can also use the concatenation operation, like for example, you can write concatenation, let us say a variable a5 comma a variable b, you can have a section defined, or an entire variable c. So, you can define a concatenation like this equal to, you can have any expression like x plus y. So, this kind of expressions are allowed provided a, b, c, these variables are one of these four types: reg, integer, real or time. But the right hand side of the expression can be anything. You can have any combination of net type variable and also register type variables, and these assignments as I had mentioned can appear only within an initial block or within an always block. So, just outside these blocks you cannot use these assignments, right. Okay. So, let us start with blocking assignment and let us try to understand what it really means. Now, the general syntax is, on the left hand side you have the variable name of the types, one of the types I mentioned, equal to, well, you can mention some kind of triggering event, like you can mention a delay, or you can also mention an event like at some clock edge or something, that also you can mention. Variable name equal to some expression. So, for the time being let us ignore this. Variable name equal to some expression, this is the general syntax, and this equal to symbol is used to indicate blocking assignment. So, what is the meaning of blocking assignment? You see, so if inside a block there are several statements, the statements will be executed one by one in the order they are specified. Like suppose inside a procedural block begin end I have 4 statements. The statement will be executed one after the other in sequence. Suppose the first statement is a equal to b plus c. So, some value will be assigned to a. Second statement is let us say d equal to a plus 5. So, that value of a which was assigned, that value of a will be used, okay, in the next expression. So, in that way one by one sequentially the instructions will get executed. This is the interpretation of blocking assignment. That means, an instruction which is executing or an assignment statement which is executing, it blocks the execution of all the statements which follow. So, unless it is finished, the next instruction will not start. Okay. This is the meaning of blocking assignment. So, the target of an assignment statement will get updated before the next statement is executed, right. But if you have several blocks, suppose I have 2 always blocks, then a blocking type statement in one of the blocks will not block any statements in the other block. It only apply to the statements inside the same block. Okay. So, this point is mentioned, they do not block execution of statements in other procedural blocks. Now, this blocking assignment style can be used to model sequential circuits also, but it is recommended that we use this assignment style to model combination logic. We shall see a lot of examples later and try to find out why this is so. This is what I mentioned. So, using blocking assignment you can also generate sequential circuit elements. So, means we had seen some examples earlier, you recall those examples where you had a multi-way branching using case, where if all the values of the case variable were not specified. Suppose I am doing a case on a variable a which can take on the values 0, 1, 2 and 3, but I specify what will happen if the values are 0, 1 and 3, but for 2 I am not specifying. So, if the value is 2, what will happen? So, all the variables which appear on the left hand side, they should not change, which means they should remember or memorize their value. So, the synthesis tool what it will do? It will be generating a latch, a storage element for such variables. But if in the case statement you mention all the conditions without any ambiguity, then it will generate a pure combinational circuit. Okay, so, earlier we took some examples to explain these things. Okay. Fine. So, an example of blocking assignment is shown here. This is not the complete Verilog module, just a segment of the module. Let us say A, B, C are 3 variables of type integer. So, inside a initial block I have this begin end. So, see the statements A 10, B 20, C 15, these are the 3 statements, one by one they will get executed. So, initially this A, B, C will be getting the values 10, then B 20, then C 15. Next statement is A equal to B plus C. So, B and C will be added, the value will go to A. So, it will be 35. So, the new value of A will become 35. The next statement is B equal to A plus 5. This new value of A will be used and 5 will be added to it. So, B will become 40, and the last statement is C equal to A minus B. So, the latest value of A and the latest value of B they subtracted and the result will be minus 5. So, this is the interpretation of the blocking assignment. Statements execute in the order they appear, just like what you see in a high level programming language like C or Java. Okay? Fine. There is one example here where various kinds of assignments are demonstrated, are shown. Here we are defining 3 variables x, y, z and 2 vectors of size 32 a, b. This is not a meaningful code, just an illustration. So, you see at the beginning we give some assignments, say x equal to 0, y equal to 0, z equal to 1. These are all single bit variables and sum equal to 1, sum is an integer. Because we have not mentioned any time delay, these assignments all will take place at time t equal to 0. Similar is the case for these 2 assignments, A 31 bit all 0 and B 31 bit hexadecimal. We initialize it with the hexadecimal number A B A B A B A B. Okay. These all they happen at time t equal to 0. Now, let us say I write at time delay 5 hash 5 A 5 equal to 1. So, the 5th bit of A will be changed to 1 at time 5. Then I give another delay 10. So, I define a segment of B, these 3 bits 29, 30 and 31, they will be assigned a value which will be the concatenation of x, y and z, and this will happen after delay of 15, which means at time 15. And lastly, sum we are incrementing by 5. So, again because there is no delay here, this will also happen at time 15. Okay. This is just an example showing how the times are kept track of in blocking assignments. Now, here we take an example of a blocking assignment and we shall show the results through simulation, because there are a few things to understand here. This is the example that we take, 4 variables defined A, B, C, D. This is a always block, always at the rate star means any variable changes, and inside this block we are saying repeat this block 4 times. So, I am saying this begin end block has to be executed 4 times and each of them will be having a delay of 5. And you see we have written a test bench which monitors the values, the time, then A, B, C and D. These values will be printed whenever some changes of these variables take place. So, we start by initializing A to 30, B 20, C 15 and D 5, and we continue the simulation till time 100. That 100 we call finish. So, let us see when you simulate this code with this test bench, what is the output. Okay. So, I am showing here this code side by side so that you can understand what is happening. You see in the test bench we initialized A30, B20, C15, D5. So, I am showing the initial values here and this is the simulation output which you got, and on color I have shown the values which are changing. Okay. So, initially at time t equal to 0, A30, B20, C15, D5 was printed. Then at time 5 this A equal to B plus C happened. So, B and C was added and A became 35, others did not change. Then again after time 5 D equal to A minus 3. So, A was 32, D became 32, 35 minus 3 32. Then again 5 B equal to D plus 10, D plus 10 B becomes 42. Then lastly C equal to C plus 1, C was 15, it became 16. Now, this will repeat 4 times. So, again A equal to B plus C, B is 42, C is 16. So, A becomes 58, D equal to A minus 3, D becomes 55, B equal to D plus 10, it becomes 65 and C equal to C plus 1, 17. So, this thing repeats 4 times, 3rd time and a 4th time. So, at the end you get results like this. Okay. So, just by simulating this code you get results like this, where the variables change like this. So, the point to note there is that every time this loop is executed, you execute them statement by statement. One statement is finished, then only the next statement starts. Fine. Now, let us look at the second type of assignment statement, namely the non-blocking assignment statement. Now, non-blocking assignment is different from blocking in the way they work, and they are more suitable to be used for specifying sequential circuit behavior, as we will see through many examples later. So, first the general syntax. Syntax is very similar, variable name and expression, but instead of equal to, we use this arrow assignment, less than, equal to, this symbol. This operator specifies non-blocking assignment. Now, as the name implies, a non-blocking assignment statement does not block the execution of the statements which follow inside that block. The statements inside the block, they can execute concurrently. This is a concept here. Okay? It is not that after a statement finishes only then the next one will start, not that. It is not blocking the other statements. So, all the statements can execute together. Okay? So, the idea is this. So, if you have a non-blocking assignment, then the assignment to the target which takes place, that will happen at the end of the simulation cycle of that block, that means at the end of the block. So, if you see here, the assignment to the target will get scheduled for the end of the simulation cycle, means the one run of the loop at the end of the block. So, here we will explain with an example. So, because it is non-blocking, statements after the instruction currently we are looking at executing will not be blocked. They will all be executing together, which will allow something called concurrent procedural assignment, which is very suitable for modeling sequential logic. We shall see this thing. So, let us take an example. As I had mentioned, this is the recommended style for modeling sequential logic, where a number of reg type variables can be assigned synchronously under the control of a common clock. But here it is just a simple example I am taking. Here this is just a test bench I am writing, there is no clock. There are 3 variables A, B and C. So, in one initial block I am initializing them to 10, 20 and 15, and in the second initialized block I am using non-blocking statement with some delay identifier. So, the idea is that when there are non-blocking statement inside a procedural block, then all these 3 statements are executing concurrently, meaning the right hand side expressions, they will be evaluating together using the current values of A, B and C, and after the delay which is specified, they will all be concurrently assigned to the variables on the left. Okay? So, in this example, let us say A is 10, B is 20, C is 15. So, on the right hand side, B plus C, A plus 5 and A minus B will be evaluated first. What is B plus C? B plus C is 35. What is A plus 5? It is 15. What is A minus B? It is minus 10. So, they will be assigned all together at time 5. So, A will become 35, B will become 15, C will become minus 10. So, you see the final value that ABC gets here is quite different from what it got when you used a blocking assignment statement. So, when you use blocking and when you use non-blocking, the results are different. So, you should be careful when you are using it to model some behavior of a system or a circuit. Okay. So, as I said that all the right hand side expressions are evaluated together based on the previous values of ABC, not these latest values, and they are assigned all together concurrently at time 5, right. So, this is a more common way where we use this kind of non-blocking assignment with a clock. This statement means whenever there is a positive edge of a clock, you compute these expressions and assign them to these variables concurrently. So, all assignments take place synchronously of a clock. You see, this is quite natural from hardware point of view, because in any hardware register there is some kind of a clock signal. So, whenever there is a clock and there is a load, the input value gets loaded. So, here also something similar can take place. The right hand side can be evaluated and the values can be made available to the input of the registers. As soon as the clock comes, all those input values will get loaded in the registers. That will happen exactly when the clock comes. Okay. So, that feature can be modeled using this POSIX clock facility. And as I said, this is the recommended style for modeling synchronous sequential circuits where there is a clock and you are wanting assignments to take place in synchronism with the clock, right. This is the recommended style. Now, let us take on one example. Suppose we want to swap the value of two variables a and b. Swapping means if a is 10 and b is 20, so we want to make a 20 and b 10, interchange their values. Let us look at various styles of doing it and let us see that whether swapping actually takes place or not. Okay. This is the first example I am taking using non-blocking assignment with two always blocks. Both are activated at the POSIX of clock, there is no delay. So, at time t equal to 0, just immediately after the clock edge comes, these will be executed. So, you see, because these are concurrent blocks a equal to b and b equal to a, they are actually executing concurrently. But you see, when you are simulating this, depending on the simulator, simulator will be either doing this assignment first and then this, or the reverse. So, if a equal to b is done first, then b will be going to a and that value of b will again be copied to b. So, both a and b will be getting the value of b that was there. But if this statement executes first, then the value of a is get copied to b and that same value remains in a. So, both the registers will finally get the same value, but it can be either a or b, you do not know. It depends on the simulator, how the simulator actually schedules these two operations execution, and this is called a race condition. Depending on the relative order of execution, the final result can be either a or it can be b. Okay. Let us look another example. Same one, instead of non-blocking, instead of blocking, I am using non-blocking assignments. See, here there is no problem, because these assignments will take place only when positive edge of clock comes and they will take place together. So, the right hand side will be evaluated. So, right hand side b, right hand side a, that values will be taken and they will be assigned to a and b at the POSIX of the clock. So, there is no question of indeterminism like in blocking assignment that was happening here, okay? Because here there is nothing that says that whenever the clock comes only then it will be assigned. Blocking says it will be done one by one. It can be either this or this or this, first this or this, depending on the order of execution. So, if you use non-blocking statement, then the variables will be correctly swapped, because the right hand side variables are read first. Let us say a equal to 10, b equal to 20, they will be read first, and whenever the positive clock edge comes, 20 will be assigned to a and 10 will be assigned to b. Okay. So, swapping will actually take place. Let us take another example. Suppose we are using blocking statement to try to swap. Suppose I write a equal to b, b equal to a, what will happen? Inside a same block, just try to see what will happen here. First, this statement will be executing, b will be copied to a and then this will be executing, a will be copied to b. So, both a and b will be finally getting the value of b. Okay. Because this is the first statement to execute, the value of b, if it is 20, 20 will be copied to a. So, a will also become 20. So, 20 will also be copied to b again. So, both a and b will be 20, the previous value of b. Okay. So, using blocking statement, if you want to really do a swap, you can do it like this by using two additional temporary variables T A and T B. You first this assign A to the temporary variable T A, then B to T B, then T B to A and T A to B. In this way swapping will correctly take place, but of course, you see you have to you use two additional variables. So, this example shows you that using non-blocking assignment for certain application can be very convenient, as this swapping example is one of them, it shows you. Okay? Fine. So, let us similarly simulate one example using non-blocking assignment, same example that is showed for blocking, but here I use non-blocking assignment. So, my test bench is also similar, but since here we use a clock, so I am applying a clock here. So, what you are doing? We are using the monitor to just mention what are the variables to print, then we initialize the variables, clock also is initialized to 0, and in a for while loop we are generating the clock signals. Forever is a loop which goes on indefinitely. We say that after a delay of 5 you do clock equal to not clock. So, the clock signal will be generating like this. Clock was initially 0. So, after a delay of 5 it becomes 1, after a delay of 5 it becomes 0, after a delay of 5 it again becomes 1, like this. So, a clock will be generated with a time period of 10, right. So, this forever statement generates this clock and we continue simulation till 100. There is another initial block where you say at 100 you finish. Let us see the simulation output for this example. So, I have shown this side by side for convenience. Initially A30, B20, C15, D5, that is the first value which is printed at time t equal to 0. Then just this is the statement, positive edge of the clock is coming after time 5, okay, clock was 0. So, after time 5 the first clock edge comes, right. So, at time 5 the first change will take place, the positive edge comes at time 5. So, B plus C will be assigned to A minus 3 will be assigned to D, D plus 10 to B and C plus 10 to C. What is B plus C? B plus C is 35, A minus 3 is 27, D plus 10 is 15, C plus 1 is 16. So, all the values are assigned together, you see 35, 15, 16, 27. Now, next clock positive edge will be coming after the time period 10. So, next one change will happen at 15. So, again you do this with these new values, B plus C 15 plus 16 31, A minus 3 32, D plus 10 37, C plus 1 17. You see all these values are assigned parallelly 31, 37, 17, 32, and these repeats up to the time 100. So, 95 is the clock edge that you get before 100, last change will take place at 95. So, this is how the simulation result shows. So, there are a few rules which you should remember when you are using this kind of blocking and non-blocking statements in a procedural block, and these are summarized here. You see, the first thing I told you is that blocking statement is the recommended style for combinational circuits for specifying combination logic, and non-blocking statement is a recommended style for specifying synchronous sequential circuit. So, the first thing to remember is that you should not mix blocking and non-blocking assignments together in the same block. Well, it is not that it is not allowed. I shall show you some examples later where you will show that what will happen if you mix them, but it can make the things complicated for you. Simulator or the synthesizer may allow, but this is certainly not a good design practice. You should avoid this. You use either blocking or non-blocking inside a particular procedural block. The second thing to remember is that these delays that you show or you specify, these are only for simulation. So, when you are doing synthesis, so all these delays will be ignored. So, the design which is working perfectly in simulation may not work exactly as you just want them to work in the final synthesized hardware. So, that is why you should keep these things in mind. Okay. Secondly, say a particular variable you cannot have it as the target of a blocking as well as non-blocking assignment together in two blocks in the same module. If you do it, the simulator or the synthesizer will give you a warning on an error message. Okay. So, with this we come to the end of this lecture, where we had looked at the mainly the differences between the blocking and the non-blocking assignment styles. So, we shall be continuing our discussion on these two styles over the next few lectures, because this is very important in modeling, and unless you understand clearly the differences between the two and what will happen if various types of combinations you use, it will be difficult for you to understand the interpretation or the semantics of different structures. So, we shall be continuing with these in the next lecture as well. Thank you.
Okay, you saw the beautiful explanation from the IIT professor about the blocking and non-blocking statements. Hope you have understood the significance of blocking and non-blocking statements. With this, we'll wind up today's class. If you have any doubts, you can ask me, or else you can mark your attendance. Any doubts, guys?